In this lecture, let us discuss the IIR realizations. Okay, so in the previous couple of lectures, we had talked of the process of transposition. Let us recap, okay, what we have done till now. So we talked the transposition, and then in FIR we discussed direct form 1 and direct form 2, right? Direct form 1 and its transposed structure is called direct form 2, and then we talked about cascade structure in FIR filters, and then parallel structure. So the parallel is obtained by polyphase decomposition, and in parallel in FIR does not lead to a higher speed. So this parallel decomposition or parallel realization will not help in FIR to improve the processing speed. So even if it is parallel processing, the speed cannot be increased, but the realization can be made canonic by sharing delays. And then we took an example to illustrate this. So polyphase decomposition is not normally resorted to, right? Why? Because it does not give any advantage in speeder processing. So if you take FIR filter and if you go to parallel realization, then it is not going to help you to improve the speed. But why are we doing this even though it is not speeding up the process? The reason is it is very useful in multi-rate signal processing that I have mentioned, right? In multi-rate signal processing, where decimation and interpolation do reduce the computational complexity, it offers an advantage. So that is the only reason we went to parallel realization of FIR filters. And then we said that in linear phase realization, because of symmetry, if you take a linear phase FIR filters, there is a symmetry. What is that symmetry? H of n is equal to H of capital N minus 1 minus n. Because of this symmetry, number of multipliers are reduced. Okay, so the number of multipliers can be reduced by a factor of half if the length is even, and it will be n plus 1 by 2 if the length is odd. So that's what we have seen in the last couple of lectures. And in this lecture, let us talk about the IIR realizations. I think we have already looked at one IIR realizations. Okay, that is a first order where we showed how to make it canonic. So the direct form can be applied extended to a general order. So for example, if I take a third order FIR filter, let me take a third order FIR filter. So H of z is equal to 1 plus d1 z inverse d2 z to the minus 2 plus d3 z to the minus 3, and in the numerator p0 plus p1 z inverse plus p2 z to the minus 2 plus p3 z to the minus 3. Then we decompose this into two transfer functions, namely h1 of z times h2 of z, where h1 of z is an FIR filter. So let me write p0 plus p1 z inverse plus p2 z to the minus 2 plus p3 z to the minus 3 multiplied by 1 divided by 1 plus d1 z inverse plus d2 z to the minus 2 plus d3 z to the minus 3, right? So let me call this guy h1 of z, and then this one is h2 of z. Now if you look at h1 of z, h1 of z is nothing but an FIR filter. So this is an FIR filter. And what about this? This transfer function 1 by 1 plus d1 z inverse plus d2 z to the minus 2 plus d3 z to the minus 3 we called h2 of z. Now we look up on it as a product of an FIR filter and an IIR filter. Okay, and then we realize h1 of z and then h2 of z. So we know that h1 of z is equal to y of z divided by w of z, and then h2 of z is equal to w of z divided by x of z. Okay, so that's it. So then we can realize these two individually. So if I realize h2 of first, because I would like to realize h2 of z first and then followed by h1 of z. So see, it is in the product. So h1 of z multiplied by h2 of z, I can write h2 of z multiplied by h1 of z. So first you realize the IIR part and then you realize the FIR part. So the input is x of z given to first block, and this one is w of z, and this w of z is given to the second one h1 of z, and this is h2 of z, and this one is y of z, like this. h1 of z, if you look at the output y of z, input is w of z, and h2 of z, if you look at output is w of z and the input is x of z. Now what is h2 of z? This guy. So I write down first h2 of z here. So h2 of z is equal to this one, right? So the output is w of z and the input is x of z, which is 1 divided by 1 plus d1 z inverse plus d2 z to the minus 2 plus d3 z to the minus 3, and then cross multiply. So w of z 1 plus d1 z to the minus 1 plus d2 z to the minus 2 plus d3 z to the minus 3 is equal to x of s. So again rearrange this. W of z is equal to x of z minus d1 z inverse w of z minus d2 z to the minus 2, I skipped one step, w of z minus d3 z to the minus 3 w of z. So the realization would be, I take x of z, right, then summation, the output would be w of z, and I require 3 delays. See, z to the minus 1, z to the minus 2, z to the minus 3, z inverse, z inverse, z inverse. So let me put those 3 delays here, z inverse, and then you put one more delay, z inverse, z inverse. So there are 3 delays. So I require 3 delays corresponding to d1 z to the minus z inverse, d2 z to the minus 2, d3 z to the minus 3, and I have a feedback after every delay by multiplying by a constant. The first one would be, what is that? Minus d1. So you put minus d1 here. Don't forget to keep the arrow mark. So, and then you put a summer here like this. So this gives you, this goes to this adder. The second one would be minus d2 the multiplier, and then you put another summer here like this, and the third one would be minus d3 like this. So this is the realization of h2 of z. If I want y of z, then I have to realize also h1 of z, which is FIR. And FIR, we know it's very easy, okay? That's very simple, and that we have already seen. Now, what is h1 of z? h1 of z is y of z divided by w of z, which is equal to p0 plus p1 z inverse plus p2 z to the minus 2 plus p3 z to the minus 3, isn't it? So y of z is equal to p0 w of z plus p1 z inverse w of z plus p2 z to the minus 2 w of z plus p3 z to the minus 3 w of z. So w of z is multiplied by first p0, right, and then z inverse. So this is p0, then you put a delay here, you multiply by p1, okay. So you put an adder here, and then multiply by p2. Before that you need one more delay, so p2, put one more delay, z inverse, and I'm sorry, I'm not supposed to use a square here, I should use a circle for multiplication, p2 p3. Okay, this is y of z, and this is the realization of h1 of z. Now cleverly I can combine this second figure and the first figure. Can you see how? See, this is the point w of z, and w of z is delayed by one delay unit here. So here you will get z to the minus 1 w of z, and here you will get z to the minus 2 w of z, and here also you will get z to the minus 3 w of z, isn't it? Similarly, if you look at here, this point is w of z, and in this point you will get z to the minus 1 w of z, and in this point z to the minus 2 w of z, and here z to the minus 3 w of z. So the same thing I am getting here also. Therefore you can take this figure, instead of using separate delays, here one delay, here one delay, here one delay, you can put this point, let's say point 1, point 2, point 3 and point 4 to this corresponding point. Point 1 will come over here, point 2 will bring it here, point 3 bring it here, point 4 you bring it here. Your job is done. So instead of using separate delays, you bring it here. So now your next diagram will be, if you combine these figures A and B, you will get the very nice, compact, simplified figure. Okay, so from point 1 you multiply by P0, from point 2 you multiply by P1, from point 3 P2 and P3. So That's it. So this is your y of z, that's all. So it is obvious that if the numerator contains higher degree, if the denominator had, let's say, p4 times z to the minus 4, then you would have required another z inverse in this point, and p4, okay, one more z inverse and p4 or something like that. It all depends on the order of your polynomial in the numerator and the denominator. So you could also handle that problem, that is the numerator degree 1 higher or 2 higher than the denominator degree. You could also handle it by writing it as an FAR plus a proper rational function. So this is how you will realize the IIR filter. That's it. So the FAR would be in parallel with an IIR realization. That would speed up the process. Now the next question is, so it's the first part is IIR part, this part. This is the IIR followed by FIR. So first you implement IIR and then followed by FIR. So if you arrange in this parallel form, then you can speed up the process. Now if the numerator degree is greater than the denominator degree, then you write this polynomial h of z as FIR plus proper IIR. Okay, if you write in this format, then it would speed up the process, because the FIR would be typically, that is, if the numerator degree is 1 higher, then it will be a linear factor. So in parallel with a proper IIR, and therefore that would speed up the process. So whenever you get a numerator degree higher than the denominator degrees, this is resorted. Okay, this is preferably decomposition, rather than adding one more delay or two more delays and taking feed forward in this point. You can add one more delay here and put a multiplier. You can put one more delay and put one more multiplier. This is P4, P5, like that also you can do it. Or you can make it like proper IIR by separating out the function, FIR function. So these are some practical points which one should remember. So whenever you get the numerator degree is higher than the denominator degree, then you write that expression as FIR plus proper IIR. What does it mean, proper IIR? When I say proper IIR, what I mean is the numerator degree, let's say n1, is less than the denominator degree n1. So whenever the degree of the numerator polynomial is strictly less than the degree of the denominator polynomial, then you say that function, that ratio is proper ratio. So always write in terms of proper ratio, and remaining things you can separate out, that is FIR. For example, if the numerator degree is 4 and the denominator degree is 3, right? So then you require 4 delays, 4 delays here. Okay, so 1, 2, 3 and one more delay, 4 delays here in the direct canonic. On the other hand, what you require is, if you decompose this in the numerator 4 and the denominator 3, if you decompose this into a first order factor plus, okay, you decompose this, then decompose like FIR, then followed by an IIR, then this will be of degree 3, numerator also 3, and then this FIR will be of degree 1. That's what I written 1 here, and therefore one delay is saved, not in terms of hardware. you recover 4 delays, 1 delay in the first order FIR and the 3 delays in the third order IIR. So the numerator is 4 and the denominator is 3. So this is improper fraction, and make it fraction by a first order polynomial plus an IIR, where the numerator degree is 3 and the denominator degree is 3. Now they are this, you know how to realize it, but the delays are in parallel, so they delay in parallel. Therefore the result would be available after 3 seconds, not 4. The processing time would be 3 times the sampling period, not 4 times. Okay, so if you put a delay in this part here, if you put a delay here, then it is not 3, it is 4. So this is not a realization of FIR. This is the realization of IR, which is decomposed into FIR and IIR in parallel. That's how they speed up the process. But totally FIR filter, parallel decomposition affords no advantage with regard to speed, that we already discussed. Now if I take the transpose of this figure, this one, okay, this figure, if I take transpose of this, what will I get? What kind of structure we will get? So in this case we will get first h1 of z, and then feed forward, that is the FIR part, then we will get the IIR part. Okay, so it is very easy to draw the diagram, so I will only draw the diagram of the direct canonical transpose form. So what is the first step? First step is interchange the input and output. So y of z is here and x of z is here. Now the pickup node becomes summing node, and summer becomes the pickup node. So here you put a summer here. See, the diagram is here, so I can't, yeah, this point becomes the summer and this point becomes the summer, this also becomes summer and this also becomes summer, and this summer becomes pickup node and this becomes pickup node. These all are pickup nodes. So that's what I'm going to draw here now. Okay, so in this output, input and output are interchanged, and then you need 3 delays as we did previously, and then in between there was a pickup node that becomes the summer node now. Then you put one more delay, then one more summer, one more delay. Z inverse. Okay, so in this case I need a P0 multiplier, so I forgot here P0, and then this point becomes a pickup node. So here you have another multiplier P1, and then P2, then P3. Okay, and in this side, left hand side, same D1, and here D2, and here minus D3. Is that right? What did I do here? Yeah, minus D1, minus D2, minus D3. I'm sorry. Minus D1 minus D2, then this summer node becomes the pickup node, multiply by d1 and give it to the summer, and then multiply by d2 and then give it to the summer, and then d3 and summer. That's it, right? So this is a transpose form, and generally we always keep the input in the left hand side and the output on the right hand side. So you have a feed forward path first, okay, p0, p1, p2, and then p3. So just transpose this, just change the flip over. So you put x of z here and then y of z here, multiply by p0 like this, y of z, and then p1, okay, p2, p3. It's a pickup node. Now this is given to the summer. So we need this p1 multiplied by x of z is delayed by 1 time unit. So you put a delay here. Okay, and p2 must be delayed by 2 time units. So you put one more delay here. That's it. Put one more delay, z inverse. Okay, and this output is multiplied by minus d1, give it here, minus d2 and minus d3. That's it. So this is the transposed structure. Okay, we need p1 z inverse in this point, p1 z inverse, p2 z inverse, p3 z inverse, and then you realize h2 of z. So output of h2 of z will be this y of z. So for h2 of z we look at feedback path. So d1 times y of z. So this d1 times z inverse of y of z. So you take a multiplier d1, okay, minus d1. So I put minus d1 here. This is minus d1, minus d2, and so on and so forth. See, in the denominator we have, if you look at here, in the denominator we had positive here. If we have positive, then the multiplier would be what? Minus. Look at here, the multiplier would be minus. In case if the denominator all are negative, this all are negative, then what would have been happened? This multiplier would have been positive. This will be positive and this will be positive. So it is a very easy to transpose a direct canonic structure. As I said, there is a value for obtaining alternative structure. Why are we obtaining this alternative structure? Because every structure has its own characteristic signature on, if you remember, on word length effects and overflow phenomena. Okay, so the direct form has certain amount of word length effects and overflow. If you realize the same structure in the transposed form, then it may have certain amount of word length effects and overflow. So for that only one reason we are taking the transposed form. And you should explore the possibility of minimizing these two. If there is overflow, if you cannot check overflow, then you can either take a costly solution, that is change from fixed point to floating point number system. It is a very costly solution. Fixed point is much less expensive. Or you should scale, that is a better solution, okay, because scaling does not require multiplication. So multiplication operation is the most costly operation in terms of speed up processing. Multiplication is repeated addition and therefore it takes time. So that's it. Now let me stop here. In the next lecture we will discuss the cascade realization of IIR filter. cascade IIR realization, that we will discuss in the next lecture. Okay, thank you.